Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we have started our discussion on MIMO receivers, that is receivers for multiple input, multiple output wireless communication systems, and specifically we had started looking at linear receivers. We said the system can be modeled as y equals hx plus n, where h is the channel matrix, and we wanted to design receivers for this. We said a zero forcing receiver for this system can be denoted as x hat, that is x hat is the estimate of the transmitted symbol vector, is given as x hat equals h t h, that is h transpose h inverse h transpose, that is y. That is, I take the received vector y, pre-multiply it by h transpose h inverse h transpose, and perform my decision on that vector. That is my estimated vector x hat, and this is known as the zero forcing receiver, or this is known as the zero forcing receiver technique. However, we said that the zero forcing receiver has some problems. More specifically, it results in noise enhancement. Hence, we wanted to move to a slightly better receiver, and we said we want to consider an MMSE receiver, or a minimum mean squared error receiver for a wireless communication system, and that receiver is simply given as follows. If we look at it, we want to minimize x hat minus x norm square, but look at this, we are minimizing this in the average, that is, we are minimizing the expected value of norm x hat minus x square. Further, we said that x hat is given as c transpose y, that is, it is a linear estimate, because look at this, this is a linear function, this is a vector c transpose times y, hence this is minimum mean squared error and also linear. It is also known as the LMMSE, or the linear minimum mean squared estimator of x. We started our derivation of the linear minimum mean squared error. We will start looking at this product c transpose y x minus c transpose into c transpose y minus x transpose, that is, this is nothing but c transpose y minus x whole square. We said this is given as c transpose y bar c bar vector c minus x y transpose c minus c transpose y x plus x x transpose. We also saw that this is nothing but expected y bar transpose is r y, expected x y transpose is r x y, expected y x transpose is r x y transpose. It is also r y x, that is the correlation between vector y and x, which is also r x y transpose. Hence, using that simplification, coming back to this, I can write this as c transpose r y times c minus x y transpose is nothing but r x y times c bar minus c transpose c bar transpose y x transpose, which is nothing but r y x plus x x transpose, which is nothing but r x x. That is, when I take the expected value of this, that is the expected value of the error, I want to minimize the average error. Hence, I am considering the expected value of this error, and the expected value of this error reduces to this function, that is c transpose r y c minus r x y c bar minus c bar transpose r y x plus r x x, where these are the respective correlation and cross correlation matrices that we introduced earlier. So, let me rewrite this again. This can be written as c bar transpose r y c bar minus r x y c bar minus c bar transpose r y x plus r x x I want to minimize this. This is the mean squared error. I want to minimize this. Also observe that R x y times C bar is nothing but C bar transpose R x y transpose, which is R y x. Hence, I will write this as, which is the same again as this term. Hence, I will write this as a succinct expression, which is C bar transpose R y y C bar minus 2 C bar transpose R y x plus R x x, and I want to minimize this. This is my mean squared error. If you want, if you can see, this is clearly a function of C. This is clearly a function of the vector C bar, that is the vector, the linear combiner that we want to use for the estimation of x. This mean squared error is a function of that vector C. I want to choose that C vector, that combiner that minimizes this mean squared error. So, what needs to be done is fairly obvious in this context. I need to differentiate this error as a function of vector C bar and set it to 0. That is what we had done earlier also in the zero forcing case, except now that we are considering the average error. So, I am going to differentiate this with respect to C, vector C, and set it to 0. So, dou f by dou C bar equals 0 for minimum. Okay. Now, the derivative of this, we had seen vector differentiation earlier before, is nothing but the differentiation with respect to each component of that vector, and this can be written as 2 R y y C bar minus 2 R y x equals 0. Remember, earlier we said derivative of C transpose R y x is nothing but R y x, that is derivative of C transpose times some vector is nothing but that vector when I differentiate it with respect to C. Hence, the C, the minimum C is such that R y y C bar equals R y x, and hence the optimal C bar that minimizes the mean squared error is C bar equals R y y inverse. The C bar that minimizes the mean square error is nothing but the solution of this equation. Hence, that C bar is R y y inverse R y x. This is the optimal. This is the minimum mean squared, linear minimum mean squared error estimator for the quantity x. All right. So, this C bar, which is equal to, let me write that down here clearly, C bar equals R y y inverse R y x is the linear minimum mean squared estimator, that is the LMM, linear medium mean squared error, that is LMM SC estimator. Okay. So, this is the expression for the LMMSE estimator. All right. And we knew that once we know C bar, the estimate is nothing but x hat equals C bar transpose times y bar. That is, I compute this vector C bar, and whatever vector y bar I receive, I multiply C bar transpose times y bar, that is my LMMSE estimate. Now, there are two things. First, here I have done this example for real vectors. It can be generalized to complex vectors in a fairly straightforward way, and except that instead of this transpose I use Hermitian. So, the LMMSE estimator for complex vectors is nothing but x hat equals c bar Hermitian y bar. Second is slightly a subtle difference, subtle extension. What I have done it is I have done this example for a case where y bar is a vector and x is a scalar. However, this expression holds perfectly well where y bar and x bar are both vectors, in which case C is a matrix. All right, that is our case, because remember in a MIMO system y bar the received symbol vector is a vector, x bar the transmit symbol vector is a vector. What I am saying is, although I have not shown you the proof explicitly, the same expression can be used, that is x hat equals r x y into r y y inverse into y bar. I am saying this expression can still be used when y bar and x bar are vectors. All right. So, now we know how to construct the MMSE vector, MMSE estimator. Let us see how to derive these quantities and how to derive the MMSE estimator for our given MIMO system. So, first let me go back to the system model. Our system model we know is y bar equals h x bar plus n bar. Hence, expected, now first let us start with expected x bar Hermitian, expected x bar Hermitian. This is nothing but the covariance of the transmitted symbols. Alright, expected x bar Hermitian is nothing but the covariance of the transmitted symbols. This is also termed as the transmit covariance. Okay, so this is also termed as a transmit covariance. This is nothing but I can write this as expected. Let me expand these vectors out. X bar is a t dimensional transmit symbol vector. So, this is x1, x2 up to xt. X bar Hermitian is nothing but x1 conjugate, that is I take transpose and row vector. Hence, this can be written as r x x, the transmit covariance is nothing but expected x1 conjugate, which is nothing but norm x1 square. So, on the diagonals we will have norm x1 square, norm x2 square, which is x2 x2 conjugate, and so on. Off diagonal we will have elements such as x2 x1 conjugate, x1 x2 conjugate, x1 xt conjugate, xt x1 conjugate, and so on. And now, if you see this expression, the diagonal terms are nothing but expected x1 square, expected x2 square, expected x norm xt square. These are nothing but the transmit powers, because if I take x1 x2, if I take x1 square, norm x1 square, average it over a large amount of time, that is nothing but the transmit power. Hence, the diagonal terms are the transmit power. The off diagonal terms are the correlation between the symbols transmitted on the different transmit antennas. Now, if the symbols are uncorrelated, which is a reasonable assumption, because you want to transmit independent in spatial multiplexing, you want to transmit independent symbols on the transmit antennas, because you want to transmit more information, that is you want to transmit independent information symbols, which means these different symbols are uncorrelated. Hence, the cross correlation x1 x2 conjugate, x2 x2 conjugate, xt x1 conjugate, all these expectations are in fact 0. Hence, this has a very simple structure, very simple and a very elegant structure. This is nothing but PD, power of each data symbol on the diagonal, and all the off diagonal terms are 0. Okay, which is the same way of saying this is PD times the identity matrix of dimension T. Okay. So, the transmit covariance Rxx is nothing but the transmit power times the identity matrix. Okay. That is the first thing. Now, we will use this to derive the other covariance matrices. For instance, now I want to derive R y y, which is expected y bar Hermitian, which is the same thing as expected h x bar plus n bar into h x bar plus n bar Hermitian, which is nothing but expected. Let me write this down. H x bar Hermitian, H Hermitian plus n bar x bar Hermitian, H Hermitian plus H x bar n bar Hermitian plus n bar Hermitian. Now, if you look at this expression, even before simplifying this, you can see that the noise and the transmitted symbol, they are uncorrelated, because this is the noise at the receiver, this is the transmitted symbol, there is no correlation, hence this is 0. By that same token, this is also 0. So, both the cross terms are 0. What survives are expected h x bar Hermitian h bar plus expected n bar Hermitian, which is, if I simplify expected h, I take the expectation operator inside, that is x bar Hermitian, that is R x into h Hermitian plus expected n bar Hermitian. This is nothing but the covariance of the noise, and we assume that noise covariance is sigma n squared identity, that is the different noises are uncorrelated and the power in each noise is sigma n squared. Hence, this is fairly straightforward. This is sigma n squared identity, and I will now substitute for the covariance, the transmit covariance Rxx, which is PD times I, the identity matrix. That gives me a simple expression Ryy equals PD, because it is a scalar, H Hermitian plus sigma n squared I. Okay. And this is nothing but the covariance matrix of received symbol vectors y bar. This is nothing but the covariance matrix of the received symbol vectors y bar. One other thing remains, that is the cross covariance, that is R y x. Remember, to compute the MMSE estimator, we need both Rxy, which is nothing but Ryx Hermitian, and Ryy. We have computed Ryy, so we need to still compute Rxy or Ryx. So, I will compute Ryx, and one is simply the Hermitian of the other, and that is also fairly straightforward to compute. We can see Ryx equals expected y bar x bar Hermitian, which is nothing but expected h x bar plus n bar times x bar Hermitian, which is nothing but expected h x bar Hermitian plus n bar x bar Hermitian. As we know, cross correlation between the noise and x, this is 0. This is simply h times expected x Hermitian, which is the transmit covariance, which is nothing but PD times identity. Hence, this is PD times h. Now, we have an expression. We know that C bar, the MMSE estimator, is simply R y inverse R y x, which is simply PD, which is simply PD h Hermitian plus sigma n squared I inverse into r y x, which is P d times h. The P d is a scalar, so I can move it to the front of the expression. This is P d h Hermitian plus sigma n square I inverse into h c bar, which is this is the MMSE estimator for our MIMO system. This is the MMSE estimator for this is the MMSE estimator for the MIMO system, which is P d, which is C bar equals P d times h Hermitian plus sigma n squared I inverse into h, where h is the channel matrix, sigma n squared is the noise power at the receiver, P d is the transmitted data power. Now, we also know that the estimate of the symbol is given as x hat equals C bar Hermitian y bar, which essentially means P d h Hermitian h Hermitian plus sigma n squared I inverse into y bar, that is x hat, and this is nothing but the MMSE estimate of x hat. So, this is the LMMSE estimator, this is the linear minimum mean squared estimator for the MIMO system. This is the linear minimum mean squared estimator for the MIMO system. All right. So, and now let me do a slightly technical manipulation to show the equivalence between two forms of this MIMO MMSE estimator. What I want to show here is that this quantity that we have over here, if you look at this quantity that we have over here, I simply want to show that this quantity h Hermitian P d h Hermitian plus sigma n squared I inverse equals P d h Hermitian h plus sigma n squared I inverse into h Hermitian. It might seem a priori that these two things are exactly the same, but look at this here in the brackets. I have h Hermitian, here I have h Hermitian h. While h Hermitian is r cross r dimensional, h Hermitian h is t cross t dimensional, and also remember the number of transmit antennas is smaller than the number of receive antennas. That is the case we are considering, which means inversion of this matrix, which is t cross t dimensional, is simpler than inversion of this matrix, which is r cross r dimensional. All right. So, it has a nice structure. I just want to show the equivalence, and that is fairly simple. I take this inverse to that side, I take this inverse this side. All I need to show is these two are equal if and only if P d into if and only if I am taking this matrix to this side, that is P d into h Hermitian h plus sigma n squared I into h Hermitian equals, now I take this to this side, that is h Hermitian into P d h Hermitian plus sigma n squared I, and now you can clearly see when I make this simplification, I will just multiply this thing out, that is P d h Hermitian h Hermitian plus sigma n squared h Hermitian equals P d h Hermitian h Hermitian plus sigma n squared h Hermitian. You can see these two quantities are clearly equal, they are one and the same thing, hence these are equal, hence these quantities on the top are also equal. Hence, we have nothing but, when I go to the MIMO estimator, that is x hat, let me rewrite this, x hat equals P D h Hermitian P D h Hermitian plus sigma n squared I inverse y bar equals, from the derivations, from the simplification that we did above, equals P D h Hermitian h plus sigma n squared I inverse h Hermitian y bar. So, this is another expression for the MIMO MMSE estimator, a more simpler expression, and this is what you will find popularly used in textbooks. If you refer to the textbooks that we have mentioned as references for the course, you will find this definition of the MIMO MMSE estimator used more popularly, which is the MIMO MMSE LMMSE estimate is nothing but P D times P D into h Hermitian h plus sigma n squared I inverse into h Hermitian into y. Now, let me make another slight observation here. So, this is the MIMO. So, this is the MIMO MMSE estimator. Again, I repeat, both these are exactly equal. Remember, this estimator that we derived here and this one that we have here, they are equivalent, right? They are exactly result in the same estimate, is just a convenience, and one form is most commonly used. And the reason I said is that inversion of this might be slightly easier, because more commonly we have number of transmit antennas much smaller than the number of receive antennas. Let me consider this to show the main difference between a MIMO and a zero forcing receiver. For instance, in a MIMO system, consider a single input single output case, that is h equals the scalar h. Then the MIMO receiver reduces to x hat equals P D times h conjugate times P D h Hermitian, h is a scalar, is nothing but P D times norm h square, P D times norm h square plus sigma n squared times y bar. Now, if the magnitude of h is small, that is as h tends to 0, this reduces to sigma, this norm of h square is insignificant compared to sigma n squared, this tends to P D h conjugate divided by sigma n squared y bar. Hence, it does not blow up to infinity. Remember, in the zero forcing case, as h tends to 0, 1 over h progressively moves towards infinity, thereby resulting in noise enhancement. However, in this case, because there is the sigma n squared, which is also known as the regularization term, that prevents this from becoming very large, it is bounded by sigma n squared. Hence, this is bounded, it does not result in noise enhancement. So, this hence the MIMO MMSE estimator, by this simple example for the SISO case, we can show that MIMO MMSE estimator does not result in noise enhancement, thus it is superior compared to the zero forcing receiver. Remember, earlier we said there is a problem with the zero forcing receiver. The problem is it results in noise enhancement. The MIMO MMSE estimator avoids that problem. That is what we are saying here. And let me find out, let me now go to one final property of this MIMO MMSE estimator. X hat, as we already noted, x hat is given as P D h Hermitian h plus sigma n squared I inverse h Hermitian y bar. Now, in high signal to noise power ratio, let us assume that P D is at high SNR. Let me write this down, at high at high SNR PD is much larger compared to sigma n square, which means this approximately becomes PD into PD H Hermitian H, sigma n square is negligible, inverse H Hermitian y bar. This PD is a scalar. So, PD into PD inverse is nothing but 1. So, this is approximately equal to H Hermitian H inverse H Hermitian y, and we have seen this before. This is nothing but the zero forcing receiver. Okay, this is nothing but the zero forcing receiver. What happens at low SNR? At low SNR, we have first, let us write the expression PD, PD H Hermitian H plus sigma n squared I inverse into H Hermitian. At low SNR, PD is negligible compared to sigma n squared. Hence, this results in PD into sigma n squared I inverse into H Hermitian y bar, which is nothing but PD, I inverse is I, PD over sigma n squared into H Hermitian y bar. If you remember this is looks similar to the MRC, that is we had for a single input multiple receive, we had received X is nothing but H Hermitian Y. So, this is nothing but a match filter. So, I claim at high SNR, this is an approximation, let me write that this is an approximation at low SNR, at low SNR. So, at low SNR, it reduces to a matched filter. So, the MIMO MMSE estimator has a very interesting property. At high SNR, if I look at the MIMO MMSE estimator, so I write at the MIMO MMSE, or in fact the LMMSE estimator at low SNR and high SNR. At high SNR, it reduces to the zero forcing receiver. At low SNR, it reduces to the MF, the maximal ratio combiner, but the maximal ratio combiner for a MIMO system, which is simply H Hermitian, the matched filter. It reduces to the matched filter, the matched filter. Receiver. So, we have seen in summary, in linear receivers, we have seen two receivers. One is the zero forcing receiver. We said that it is slightly it is simple, but slightly inferior because it results in noise enhancement, and then we have proposed a robust MIMO MMSE receiver, and this MIMO MMSE receiver has this interesting property where at high SNR, first it does not result in noise enhancement, and second, it has interestingly at high SNR it reduces to the zero forcing receiver, low SNR it reduces to the matched filter. Okay. So, that completes the discussion on MIMO linear receivers. There are also MIMO non-linear receivers. However, I will defer that discussion to slightly later. First, we have to cover something that is slightly more important, which is the decomposition of a MIMO channel. So, next we are going to start with a very critical aspect of MIMO, a very key aspect of MIMO, which is a key to understanding all the properties of a MIMO wireless communication system, which essentially is the singular value decomposition of a MIMO communication system. So, let me talk about, so let me start with the decomposition of the MIMO channel. So, we are going to talk about a decomposition of the MIMO communication channel, of the MIMO channel matrix H. In fact, specifically we are going to look at one specific decomposition, that is the singular value decomposition. We are going to look at MIMO SVD, where SVD equals singular value decomposition. So, we are going to talk about MIMO SVD, where SVD stands for the singular value decomposition, and the singular value decomposition of a matrix, of any matrix, in fact can be expressed as follows. H, the matrix H is given as U sigma V Hermitian, where this matrices U are such that we have U is nothing but columns U1, U2, so on up to UT, that is, this has T columns into the singular matrix sigma 1, sigma 2 up to sigma T into, and this is along the main diagonal, into V1 Hermitian, V2 Hermitian, Vt Hermitian, and these are the different rows. These are the different rows. So, this has T columns. Remember, I am assuming here that R is greater than or equal to T, that the number of receive antennas is greater than or equal to the number of transmit antennas. This has T columns. This matrix has T rows, and the properties, and these are not any T columns, just any T columns are T rows, but the properties of these matrices are such that the first of all, these columns, what can we say about these columns? The columns are orthonormal, that is norm ui square, equals 1, while ui Hermitian uj equals 0 if I not equals j. That is, the norm of each column is 1, and the cross product, the dot product between different columns, that is ui Hermitian uj, which is u1 Hermitian u2, u1 Hermitian u3, u2 Hermitian u3, so on and so forth, are 0. That is, the cross product dot product is orthogonal, they are unit norm, these are known as orthonormal columns. Similarly, for the case of the rows of the matrix V, which is we say Vi square equals 1, Vi Hermitian Vj equals 0 if I not equals j. Okay. So, the rows, columns and rows of matrix U and V are orthonormal, and then you can verify it. So, this is an R cross T matrix, U is an R cross T matrix, V is a T cross T matrix. So, we have the following property, we have V Hermitian V equals V Hermitian equals identity. This is known as a unitary matrix. This is known as V is a unitary V is known as a unitary matrix, while U, the matrix U satisfies the property that U Hermitian U equals identity. Observe that U Hermitian is not equal to identity, because we have assumed R is greater than or equal to T. If R is equal to T, then U Hermitian is also identity, but the more general result is that U Hermitian U is identity. And the other important aspect is these singular values. What is the structure of these singular values? The structure of these singular values is such that first sigma 1, sigma 2, sigma t are known as the singular values. These are known as the singular values of the matrix H. They are important for any matrix H, such that further they satisfy the property. They are such that sigma 1 to sigma 2 sigma t are greater than or equal to 0. That is, they are non-negative. Either all the singular values are either 0 or greater than 0. That is, they are non-negative. Further, these singular values are ordered. That is, I cannot place them in any order, but the order is such that sigma 1 greater than or equal to sigma 2 greater than or equal to sigma t greater than or equal to 0. So, these singular values are, so this is the decreasing order. So, these singular values are ordered. This is the order property of singular values. So, we say it as singular values are ordered. Alright. So, the singular values have to be given in that decreasing order. So, these singular values are non-negative and they are in decreasing order, and this singular value decomposition exists for any matrix, including a non-square matrix. For instance, you might remember another related another decomposition which is known as the eigenvalue decomposition. However, the eigenvalue decomposition exists only for square matrices. Unlike an eigenvalue decomposition, a singular value decomposition exists for matrix of any dimension, that is also non-square matrices, as we are going to see some examples. For instance, let me take a simple example of a 2 cross 1 matrix. So, let me take a simple example of a 2 cross. So, let me start with some examples. Singular value So, let me start with some examples of singular value decomposition. Let us consider with a basic example, that is, I consider a matrix H equals 1, 1. This is a 2 cross 1 matrix. This is essentially a 2 cross 1 matrix, corresponds to when you have 2 receive antennas and 1 transmit antenna. Remember, this matrix is a 2 cross 1 matrix, it is non-square, it does not have an eigenvalue decomposition, okay, which means, however, it still has a singular value decomposition. That is what we are going to show, and this also satisfies our criterion that R is greater than or equal to T. I can write this as equals 1 over root 2, 1 over root 2 into the singleton matrix square root of 2 into the single dimensional matrix 1. Alright. Now, I claim this is my matrix U, this is my matrix sigma, this is my matrix, this is my matrix V. Alright. So, I claim this is my matrix U, this is my matrix V. Now, why is this my matrix? Why is this satisfies orthonormality? For instance, if we take the vector 1 over root 2, 1 over root 2, we can see that the norm of that vector, if I take u1 equals this thing, I can see that norm u1 square equals 1 over root 2 square, that is half plus half equals 1. Okay, so, this is unit norm. Further, if you go seeing the singular value of this is square root of 2. So, the singular value sigma 1 equals square root of 2, there is only one singular value and it is greater than equal to 0. And further, the matrix V, it is trivially a unitary matrix, because if you look at this matrix, V equals 1, which means V Hermitian equals V Hermitian V equals 1, which is essentially identity matrix. Hence, this is a trivial singular value decomposition. We have shown that singular value decomposition exists for a non-square matrix. Okay. So, this is a singular value decomposition, a simple singular value decomposition. Let me take a slightly more what is subtle example of a singular value decomposition. Let me take an example, another example 2 of a singular value decomposition, which is the diagonal matrix 1, 0, 0, square root of 5. This is the matrix H that I am considering. Now, one might tempted to think that the singular value, since this is a diagonal matrix, the simpler value decomposition can simply be written as 1, 0, 0, 1, that is the identity matrix times 1, 0, 0, square root of 5 times 1, 0, 0, 1. Okay. So, this satisfies all criteria. For instance, this has orthonormal columns, this has orthonormal columns, the singular values are non-negative. However, this is not a valid singular value decomposition, this is not a valid decomposition, this is not a valid SVD. Why is this not a valid singular value decomposition? Because look at the singular values, these are sigma 1 equals 1, sigma 2 equals square root of 5, these are not ordered. In fact, we have sigma 2 greater than or equal to sigma 1. So, the singular values, so the singular values are not ordered, hence this is not a valid SVD. Instead, the valid SVD of this can be written as, and you can verify this, the valid SVD of this can be written as 0, 1, 1, 0, that is nothing but the identity matrix, that is whose columns are flipped. Look at this, this is 1, 0, 0, 1 is identity matrix, this is 0, 1, 1, 0 times now square root of 5, 1, 0, 0, again 0, 1, 1, 0. Now, you can see the singular values sigma 1 equals square root of 5, sigma 2 equals 1, sigma 1 greater than or equal to sigma 2. Okay. Now, you can see that the singular values are ordered. Further, you can see that the matrix, this is of course orthonormal columns, in fact, it is unitary. In fact, you can also see 0, 1, 1, 0, that is V Hermitian equals 0, 1, 1, 0, the product, this is nothing but V Hermitian, this is equal to 1, 0, 0, 1, this is nothing but identity. Hence, we have V Hermitian equals identity, hence this matrix is unitary. Hence, the matrix is unitary. So, that is a slightly more tricky example of a singular value decomposition. Let me take a third and final example to illustrate the singular value decomposition. Normally, the singular value decomposition is complicated. You cannot compute it ordinarily by on a pen on a paper. I am just illustrating this simple example so as to give you a feel of what the singular value decomposition looks like. If you want to compute the singular value decomposition of matrices in the cases when it is not straightforward, there is a MATLAB command known as SVD. If you go into MATLAB and you type SVD or you type the help section about SVD, you will find out how to use this command. So, typing that command SVD, you can get the singular value decomposition of the matrices, which you can more matrices in general, which you cannot compute by a simple paper and pen kind of computation. So, let me illustrate a third example for SVD. for a singular value decomposition, H equals 1 comma 1, 2 comma minus 2. This is, you can clearly see this is a slightly more general matrix. However, I can simplify this as 1 comma 1, 1 comma minus 1 into 1 0 0 2. That is, this matrix can be written as 1 1 1 minus 1 into 1 into the matrix 1 0 0 2. Now, again it is tempting to simply claim the singular values are sigma 1 equals 1, sigma 2 equals 2. However, there are several things that have to be taken into account. First of all, this matrix is not does not have orthonormal columns, because you can clearly see the magnitude is not 1. Also, the singular values are not ordered. So, I will first take care of ordering these things. What I will do is I will first order this by simply reordering these matrices. I can reorder these as follows. You can see and you can verify that this can be written as this matrix times again the same matrix that we had seen before, the identity matrix, which is flipped. Now, you can see that whatever these are not still the singular values, but these are ordered. Now, I need, now this matrix V here, which is 0 1 1 0, this you can see is clearly a unitary matrix, except this U matrix, it does not have normal columns. So, I will divide by the magnitude of each to make this as normal columns, and I can write this as H equals 1 over square root of 2 minus 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, root 2, 0, and now you can see the matrix U. Matrix V is orthogonal or unitary, U is also unitary. In fact, it has normal columns now, that is, the norm of each column of U is 1, and also the singular value sigma 1 equals 2 root 2 greater than equal to 0, sigma 2 equals root 2 greater than equal to 0, and further these are ordered. In fact, we have sigma 1 greater than equal to sigma 2, hence these are ordered singular values, hence this is a valid singular value decomposition. Alright, so we have looked at the singular values decomposition. Further, I also forgot to mention one small point. In fact, the number of non-zero singular values singular values is equal to the rank of the number of non-zero singular values is equal to the rank of the matrix, and you can clearly see the rank of the matrix is 1, number of non-zero singular values is 1, and in this case you can see the rank of the matrix is 2. So, number of non-zero singular values is 2. Beginning with this understanding of the singular value decomposition, we will explore the properties of the MIMO wireless communication channel in the next lecture.